Have you ever wondered how your music app can just instantly skip to the next song? Or how your browser's back button seems to work so flawlessly? Well, the secret isn't magic. It's actually a really clever and elegant data structure working silently behind the scenes. And today, we're diving deep into that structure, the linked list. But to really get why linked lists are so ingenious, we first have to talk about the problem they were designed to solve. And that problem? It starts with their older, much more famous cousin, the array. So picture this. You've got a massive playlist, right? Thousands of songs. And you decide, I'm going to delete this one song right from the middle. If that playlist is stored as an array, well, your computer is about to do a ton of work it really doesn't want to. The second you delete that song, it leaves this gaping hole in the computer's memory. So to fix this, your device has to do this massive, really costly operation that I call the array shuffle. It takes every single song that came after the one you just deleted and, one by one, painstakingly shifts it up a spot. I mean, think about it. Thousands of operations just for one simple deletion. This whole shifting process is a huge performance bottleneck, especially when you're dealing with big data sets. And it was this exact problem that made computer scientists step back and ask a really simple but totally revolutionary question. Isn't there a smarter way to do this? And yes, there is. Enter the hero of our story, the linked list. It's a completely different way of thinking about how to store a sequence of items. So what is it exactly? Well, unlike an array where everything is stored in this neat, orderly block of memory, a linked list kind of scatters its elements, we call them nodes, all over the place. The magic trick is that each node contains a pointer. Think of it like a digital address that tells you exactly where to find the next node in the sequence. Honestly, the best way to think about it is like a treasure hunt. You start at the beginning, which we call the head. The head has its data, sure, but it also has a pointer. That's your first clue. You follow that clue to the next node, which has its own treasure, and the next clue. And you keep doing this until you reach the very last node, which points to null, basically signaling, hey, the treasure hunt is over. Now, this simple idea of nodes and pointers, it's the foundation for a whole family of linked lists, and each one has its own unique superpowers. First up, you've got the singly linked list. Just think of it like a one-way street. Each node has just a single pointer, and it only points you to the next destination. You can only travel forward, never backward. It's the simplest and, because of that, the most memory efficient of the bunch. Then you've got its more powerful sibling, the doubly linked list. This one's a two-way street. Each node has two pointers, one pointing forward to the next node and another one pointing backward to the previous one. And this is incredibly powerful because now you can move in both directions. And this slide just illustrates that trade-off perfectly. A singly linked list is lean. It uses less memory with just that one pointer per node. But a doubly linked list, while it does use a bit more memory for that second pointer, gives you that awesome bidirectional travel and a real superpower, the ability to delete a node in a single step, instantly, as long as you know its location, because it already knows who its previous neighbor is. And finally, there's a fun variation, the circular linked list. For this one, imagine a racetrack. Instead of the last node hitting a dead end at null, it points right back to the very first node, creating a continuous loop. This is perfect for anything that needs to cycle endlessly. Like a slideshow or a music playlist that's on repeat. Okay, so we've got this whole family of linked lists, but how do we choose which one to use? Well, that brings us to the most important concept for any engineer, performance. Because in programming, everything, and I mean everything, is a trade-off. So here's the absolute crux of it all. With linked lists, you make a fundamental trade. You give up the ability to just jump to any element instantly, what we call random access, and in return, you get lightning-fast insertions and deletions. In computer science, we have a name for this incredible speed, O of 1, or constant time. And let me tell you, it's the holy grail of efficiency. It means an operation takes the exact same tiny amount of time, whether your list has 10 items or 10 million. It is literally the fastest an operation can possibly be. And here it is. This is the big aha moment. Just look at this comparison. Arrays are amazing at one thing, accessing an element by its index. Bam, O of 1. But linked lists? They absolutely dominate when it comes to adding or removing items from the beginning of the list. No more array shuffle. It's just an instant, beautiful O of 1 operation. But let's talk about that weakness. Why is accessing an element so slow for a linked list? Well, it's because you can't just tell it, hey, go to the 500th song in my playlist. You literally have to start at the head and follow 499 pointers to get there. The time it takes is directly proportional to the position you're looking for, which we call O of N.
So, keeping these trade-offs in mind, where do we actually see these things being used? The answer is pretty much everywhere.
You use them every single day. Your browser's back and forward buttons? That's a classic doubly linked list. The undo-redo feature in your favorite text editor? Yep, also a linked list. That next button in your music app? It's just following a pointer to the next node. Even your computer's operating system uses a circular linked list to give every single running application a fair turn at using the processor. So, why should you care, especially if you're trying to get a job in tech? Because understanding linked lists, it's a huge signal to interviewers that you actually get the core concepts of programming. It shows you can think about memory, that you can analyze trade-offs, and it's the foundation for way more advanced data structures. Trust me, it's a topic you are almost guaranteed to face.
So, let's end on a little thought experiment. A social media feed. It needs to load new stuff at the top constantly, but you also need to be able to scroll through it pretty seamlessly. So, given all the trade-offs we've talked about between arrays and linked lists, which one do you think is at the heart of your feed? It's a great question, and it really shows you just how critical these choices are in building the technology we use every single day.